All right, welcome everyone. As you probably saw in the announcement, I've gone over all of the exams and corrected any problems that I could find with the Blackboard grading system and put up solutions on those. I'm not going to go over the exam in class because most of the class did pretty well on it. The median was 25, and there was kind of, I guess, an even skew around that. I will, those of you who aren't happy with how you did, I will announce some options for you to make up and show your competency in some other ways. Keep your eyes out for that this week. Let's see. All right, so we covered in the last class some properties of probability. We're moving into probability distributions, and especially the distributions. The rest of the class from now on is going to be applications of these distributions. And I wanted to say all of the introductory stuff we've been doing so far, the descriptives, the plotting, and this probability distribution stuff, it's all kind of statistical, but it gets much easier to start bringing in public health examples as we get into some of the tests, the things that are widely used. But this is, I would say so far, a lot of background on the I guess, theory that you're going to need for understanding all of the tests that we do. So I'm going to briefly review the properties of probability that we went over last class, and then talk about the normal distribution and the binomial distribution, which will allow you to do inference for, I believe, well, not quite all of the tests that we'll cover in this course, but most of them. So as you'll recall, we use this Venn diagram notation to represent the probabilities of events occurring where there's no overlap between them like this, that those are mutually exclusive events. And the union of these is the simple sum. And you'll remember if there was overlap between them, we had to sum them and then subtract the amount in the intersection. So in this case, the union of the example being having cancer or not having cancer is just the sum of those two possibilities, and it's 1 since these are the only two options that there are. And the intersection is 0 since you can't both have cancer and not have cancer. With non-exclusive events, there's that overlap. So now if you want to do the union, you have to add up the individual probabilities and then subtract the amount in the middle, that intersection, so that you're not counting it twice. If these events are dependent, meaning that the probability of one of these things is unrelated to the other, then the intersection is simply the product of those two things. And if they are not independent, then we have to add this conditional probability term down here. Actually, I just want to take a moment and check if we have anyone attending online. Yes, we have 6 viewers. So if anyone online is having trouble, let me know, or maybe you can let me know if you're not having trouble too. Just send me a question to let me know that you can hear us fine. Okay, good. They're hearing us loud and clear. Okay, here's your probability notation cheat sheet. I won't go over this again, but keep it handy. All right, moving on to the new material. A random variable is something where we can measure and categorize it. It has definitive outcomes, but those outcomes aren't certain. So any particular outcome, it's not deterministic. There's at least an element of chance to it. So the number of new diabetes cases in New York City in a given year, if we're talking about last year, it's a given number. There's nothing probabilistic about that. But if we're talking about this year or next year, it's a random variable, because it will have a particular realization, but we don't yet know what it is. And the kinds of variables I was talking about before, the categorical, discrete, continuous, those are classes of random variables. Any questions so far? All right. So I put a bunch of notation. You'll see this in the syllabus. Keep me to it. If I forget to do this at any point, feel free to ask me, but I want to be very consistent with notation so that it won't confuse you about what I'm talking about. So the random variables will be uppercase, and realizations of those random variables will be lowercase. So in that example of the number of diabetes cases in New York City last year being a certain number, that's a lowercase. But if I talk about the probability of the number next year being greater than a certain number, that'll be an uppercase, because that's a random variable where we don't know the outcome of it. All right, a couple examples. Blood type. So these are prevalences of blood types in the US. So if we have a count of everyone, that gives us an estimate for the entire population, but we don't know if someone comes into a blood donor clinic, we could describe their blood type before we measure them as a random variable. And what kind of random variable is it? Categorical? I hear, yep, categorical. So do you get that distinction there between the random variable? I'm a type A positive, that's not a random variable. But if I were to ask the question of how many A positive blood types are in this room, that we could call a random variable, because we would know something about it from this. You know, on average, it'll be about 35.7% of you, but it's not going to be exactly that. There's some uncertainty in that, which is why we call it a random variable. The number of visits to an obstetrician's office during an uncomplicated pregnancy. When a new patient or a pregnant woman goes into an office, the office does not know how many times that that individual will visit the office, but they have some idea based on past experiences, and they might use this information, this sort of prevalences of numbers of visits, to calculate if we have 100 new patients coming in each month, how many can we expect to come back in for visits over the next X number of years. So that's using a random variable, which is the number of visits, to estimate and give a range on something practical. This, of course, is a quantitative variable, and it is discrete because it only takes integer values. The distribution of body mass index in a population. This can take any decimal value. So this is a continuous variable. And it's a pretty well normally distributed continuous variable. So we're going to be doing a lot of drawing of probability distributions of random variables, and this is usually how we're going to do it. We're going to put an interval along the x-axis and put either probabilities along the x-axis or numbers like we have on the right here. And this y-axis is a probability. I'll talk more about that. So you'll notice this is not discrete. This is not like the histogram. This is continuous because we're talking about a theoretical random variable here. We're not going to be so much interested in what this y value is at a given point, but we're going to be interested in intervals along the curve, like these shaded areas. You'll be doing lots of calculations of calculating the area in certain intervals. Yes? Oh, got a question. Okay. So does anyone know if we went all the way across the limits, say here from -infinity to infinity, what the area under this curve is if the y is representing a probability? 1. Yep. So any interval that does not include the limits is going to have a probability somewhere between 0 and 1. If it's an infinitesimally small interval, its area will approach 0, or its probability, and as it gets larger, it'll increase from 0 until eventually it's 1. And as I mentioned, the interval containing all possible values, its probability adds up to 1. Okay, so not everything is normally distributed, but as we're going to get to in the next class with the central limit theorem, turns out that all sampling distributions are normally distributed once you get to a large enough sample size, which is what makes this such an important distribution. A lot of things occurring in nature are normally distributed, so it's also important in terms of populations, but in terms of statistics and statistical inference, it's even more important. And for binary outcomes, anytime you have a binary outcome, a yes, no, heads, tails, healthy, sick, and you have a number of independent events of that. So are you going to get the flu this year? There's a certain probability, yes or no. If all of our probabilities of getting the flu were independent, which they're not because we're coming to class together, but if they were, the expected number of people who would get the flu this season in this classroom would have a binomial distribution. So, a few things about the normal distribution. It is symmetric, so if you draw a line at this highest point, it is identical going to the left and to the right. You can put a mirror there and reflect it, and it looks exactly the same on the other side. It's characterized by only 2 numbers, the mean and the standard deviation. This center, this maximum, that is the mean, and the standard deviation impacts its dispersion, how wide it is. So here are a few examples. We have 3 of these curves with a mean of 0. They're centered on 0 here, which you can't quite see because we have something blocking it. See if I can move that. That's better. What's that? Oh, there should be more. Does anyone have the handout still? Okay, so we have these three here with a mean at 0, one with a mean at -2. You see how that just shifts the whole thing over. We have a few different values, the standard deviation squared, the variance. The red one has the smallest standard deviation, so it's skinny. This purple one has, this blue one has the largest, the 5, and that's nice and broad. That's pretty well what you need to know about the standard or about the normal distribution. There's a little bit more. We'll get to it. So here's a real life example, heights of men and women. In the US, women have approximately a mean of 65 inches and men 70, with a standard deviation for women of 3.5 and for men of 4. So it's shifted over to the right and a little bit wider for men. Okay, so there are a couple more things to know about this, the normal distribution. One of them is the empirical rule. This is an easy way to tell whether some data that you have are approximately normally distributed. So starting from the mean, if we go to plus or minus 1 standard deviation, that contains 68% of the probability, or 0.68 out of 1. Going to plus or minus 2 standard deviations, we get up to 95% or 0.95 probability. And going to plus or minus 3, we've got 99.7 or 0.997 probability. So if you have a lot of data with more than if you go plus or minus 3 standard deviations and you see much less or much more than that at any of these points, that's an indication that you're not normally distributed. Quick question. If we go from the center to 2 standard deviations to the right, so from here, see if I can draw on this slide. So from the center to here, how much area is that? What's that? 47.5. Yeah, 47.5. Because it's symmetric, so it's 95 between +2 and -2, and half of that is 47.5. All right. So in the example of heights of adult men and women, for women it was 65 inches and a standard deviation of 3.5 inches. We apply this so-called 68, 95, 99.7 rule at the 1, 2, and 3 standard deviations. We find 68% are between 1 standard deviation, so 65 plus or minus 3.5, and 95 between 58 and 72, and 99.7 between 54.5 and 75.5. So it would be pretty easy to tell if you have a bunch of data that are supposed to be heights of women, and you maybe find that you can first test what the mean is, what the standard deviation is. This is a very qualitative test. This is not a test of inference, but in your descriptives, you could say if much more is within, then 68% is between these bounds, it's probably a skewed or a more, some fatter tailed distribution. All right. Do you feel like doing some hand calculations? You don't have to. You can just go on, but I don't know. It's kind of fun. So what proportion of women are less than 68.5 inches tall? And I think the, let's see, the mean was 65, and the standard deviation was 3.5. Oops. Yeah, so let's see. You draw something like this. No. This is a good habit to get into, drawing little sketches like this when you do your inference tests. It's, for some of the tests, it's not a big deal. For the so-called two-tailed tests, it's fairly formulaic, but we are going to cover some one-sided tests, and I can guarantee that some of you are going to get confused with the one-sided tests if last year was any indication. And one of the best ways to avoid making a mistake on this is to draw a diagram like this, so that you're not calculating this area when you need to be calculating this area, for example, just to keep things straight in your mind exactly what, because you know, everyone knows in statistics you calculate p-values, but it's kind of easy to forget what those p-values mean, and those p-values correspond to shaded areas on curves like this. Okay, so standard normal distribution can have any mean and any standard deviation. Standard deviation has to be positive. That's the only limitation on it. Mean can be anything. But there's only one standard normal distribution, and you can convert any other normal distribution to the standard normal. All you have to do is subtract its mean and divide by its standard deviation. This has a number of names. It gets called z-scoring. Sometimes it is called studentization. Sometimes it is called standardization, but it's a process of converting anything that is normally distributed into the standard normal distribution. And this is what the standard normal looks like. It's a little small here, but instead of something like 65 at the center, it's always 0 at the center. And if you go up to 1, this will contain 68% between -1 and 1, 95% between -2 and 2, etc. So all it is the normal distribution with mean 0 and standard deviation 1. Worth noting that it looks exactly the same. So if you have some observations, you sometimes even standardize or z-score observations. The shape of them stays exactly the same. All it does is shift your axes. So it takes whatever numbers you had here and changes it so that it's basically a scaling of your data or your distribution. The main reason that we do this is because there are tables of the z distribution, of the standard normal distribution. There's one in your textbook, Appendix B.1. This is, I took a screenshot from this, and it has values you can look up for negative z and for positive z, and it's giving you the so-called left tail distribution. it's a lot of textbooks and tables actually don't give you both. And you know, it's not necessary to give you both of these. It's kind of convenient because you can just look up whatever Z you have and find this left tail probability. But what would you do if you needed this and there were no positive Z's in your table? You only had this one. Mm-hmm.
You just use symmetry. Do 1 minus thing.
Yep. Yep, that's it. It's symmetric. So the probability of this area you could calculate. So you need a tail that does not include the center. So you could calculate something like this. And then the other thing you need is that the probabilities sum to 1. So this, once you've calculated this area, you would just go 1 minus that. Yes, question?
If we can go back to slide 18.
18.
And the equations.
Yes, the equation on slide 18.
That X there, is it a probability of an event, or is it something else? What does the X stand for?
So the X would be the realization of the event. It would be like a BMI, like a height, but it's a distribution of BMIs or of heights. So it's a thing. It has units. It's not a probability itself. So in this example, say of heights, X is the distribution of women's heights. So that has mean, I forget what it was now, 65, and standard deviation of 3.5, was it? That's what X is, and it depends on the units. So X is one variable in inches. It would be, you know, it would have different values if you're doing it in centimeters. But it is the thing that of interest, the measurable, observable thing. And then we talk about probabilities of that thing, that random variable being in certain intervals.
What is the mu in that case then?
Well, so I use mu to be population values. So in this case, I'm talking about like the women's heights where we know what it is for the entire population. The known, right.
That X is the random variable that you are measuring.
Right. Yeah, X is the random variable that we measure. There are some cases where we know the population parameters, like women's heights, we know what it is. So even if we only observe 10 people here, we could use something that came from a national study and gets this very accurately for us. Same with the standard deviation. That's actually a very important clarification though, because it turns out we will use different tests depending on whether this standard deviation is estimated from a sample or whether it's known from the whole population. That's the difference between the z-test and the t-test. Have I clarified this question for you?
Yeah.
Yeah. Any other questions? We've got time. We're not in a rush today. So. This is just an example of looking things up in a Z-table. You're going to get some practice doing it downstairs after this class. This is almost just like the one in the text. I copied another one because it had a larger font. But anytime you need to calculate a probability and it doesn't fall somewhere on that empirical rule, you'll have to use a table. So for something that is, if we want the probability of observing a height that is less than 1.43 times the standard deviation, or 1.43 standard deviations above the mean, then we'd have to use a table. In this case, this is a left tail probability like shown here. And you have these rows, you have these columns. You follow the rows until you get the first decimal place, and then go across till you get the second decimal place. So the answer here would be that the probability of an observation 1.43 standard deviations above the mean or less is 0.9236 or 92.36%. You do a bunch of looking stuff up in the tables and in the first year of class. After this, you'll probably only ever use software, but the hope is that by knowing how to do it this way, you're less likely to interpret the software output wrong. Question?
What if they ask something like the standard deviation of 1.33?
Mm-hmm.
Can we find that also on the table, or do we have to calculate that out?
I mean, question is if the standard deviation is 1.33 or 1.33 standard deviations.
Standard deviations away from the mean.
Yeah, you can still use, so 1.33 would be this value right here.
Oh, okay, I can see the top row.
Yeah, there are some skipped here, but this will give you an accuracy of 2 decimal places in Z. You can do this in Excel. I know how to do it. I'm not actually sure you can look up a probability of the standard normal in SPSS. You definitely can in Excel. I think I even put in here the command for doing it. And of course, the right tail probability here, even though we don't look it up directly in the table, is just 1 minus this left tail probability. So 1 minus 0.9236, 0.0764. There are a few important Z values, although the one that you're gonna see over and over until you probably won't forget it is the 1.96. The probability of the standard normal distribution being greater than, of a realization from the standard normal distribution greater than 1.96 is 0.025. That turns out to be important for building 95% confidence intervals and for doing statistical tests where you consider a p-value of less than 0.05 to be significant. And that difference between the 0.025 and the 0.05 has to do with whether we're looking at 1 tail or 2 tails, but that's for later. The norm.dist function in Excel, that will let you look up a probability for any value of Z. One more example here. So those were one-tailed examples, but there are cases where you want something bounded on the left and on the right side. All you have to do to calculate this probability is to calculate the left tail probability of the right-hand side and of the left-hand side and subtract them. If these happen to be centered on the mean, then here you'll see the means subtract off, and it doesn't matter, but you can also do this for asymmetric areas, say between between here and here. So see in this example, the probability of z between minus 1.43 and 1.43 is just probability of z less than 1.43 minus probability less than minus 1.43. Works out to 0.85. The other way to do this would be to calculate this left tail probability, the probability of z less than minus 1.43, and just doubling it. And that's something that we can do because it's a symmetric area. And of course, we couldn't do in this example. It's only because same amounts on the left and right. Okay, so as I mentioned, my suggestion when you're doing statistical tests, solving problems, go ahead and draw these curves out and shade in the area where you need the probability, especially if you're ever doing one-sided tests. It can be really easy in those cases to use the wrong, look up the wrong value of z if you're not drawing it out. All right, I think we need the more examples. So that example, the couple examples I gave were where we have a certain value and we want to get a certain realization of the random variable, and we want to get the probability of observing that or greater or that or less. The reverse situation also comes up where we have a certain probability and we want to find out the value of a random variable corresponding to that probability. So we want, for example, the interval centered on the mean that contains whatever that was, 87% of the probability. And then we're basically going to do the same thing in reverse, but looking up the in the table in reverse. So you would find this probability. So if we wanted 0.0764, you actually look in the table, find that value of z, figure out that this is minus 1.43, and you can give this interval. This is called the quantile. You know, of examples that of like this of quantiles, like test scores. If you want the 95th percentile of SAT scores, you would need to find the point on that random variable of SAT scores below which 95% of the probability lies. So it's called a quantile or percentile if you put it into percents. Okay, this important example, find the value of z for a cumulative probability of 0.975. I don't know if you have I don't think you have it handy. Look this up when you go downstairs. But if you go to the 0.975, you'll find that it is at z equals 1.96. So this is going in the other direction to calculate a confidence interval. You'll probably get kind of used to just using the 1.96 and the 95, but you can calculate any confidence interval, and you might want a 90% or a 50% confidence interval. All right. So we're talking at this point about individual observations. We're not going to get until next class into samples. So we're talking about populations and individuals in the population. And when we do this, I'm going to ask questions like, suppose women's heights have this distribution, this mean, this standard deviation, what is the probability that, that one particular individual is taller than this? And to do that, you're gonna write it out as follows. So this is the probability that our random variable x takes a value less than this particular realization, lowercase x. So the height example would be probability that x is less than 65, where x is that random distribution of women's heights. Next step, if you're going to use a z-table, is to standardize it. So you rewrite it in terms of the standard normal distribution. So you want the probability of z being less than the z-scored observation. So you take that observation, subtract the mean, divide by the standard deviation, and then write the problem again using z. Draw your picture and then find the area. Okay. Sorry if I'm belaboring this. Binomial distribution. So we use the binomial distribution for random variables where individual events take a binary value, yes or no, sick or healthy, has or does not have cancer. So individual observations can only take one of two values, but we look at numerous outcomes, so of repeated independent events. And then it is the count of the numbers of each of those outcomes that is binomially distributed. So as an example, we have 100 randomly selected individuals in New York City. What's the probability that that exactly 60 of them, or 60 or more, something like that, have private health insurance? So the random variable itself, this is a bit more confusing about the binomial distribution. The lowercase x is just yes or no, but the random variable, the capital X, is a number. It's an integer number. So in this case, the random variable, capital X, can take values anywhere between 0 and 100. And the individuals are either yes or no, or when we code them 0 or 1. So it's a little bit different than with the normal distribution in that sense, in that in the normal distribution they're on the same scale. With the binomial distribution, they're not. Does that make sense? All right, so again, we call these trials, and when there are numerous of these outcomes, we call it a Bernoulli trial, although that doesn't matter too much for you guys. But it's a series of independent random events, like a coin flip, like someone getting sick or not. And the key here for using the binomial distribution is that the trials are independent of each other. And if that is the case, then our probability of X successes and N trials, and we use the word successes even though it, and not in all cases do we really have such a thing as a success and a failure. But that is the terminology of Bernoulli trials. This is the probability of exactly X successes in N trials. So in the example of the private health insurance, with N equal to 100, this would be a very large number, 100 factorial. So that's 100 times 99 times 98, etc., all the way down to 0. And it's divided by, in that case, we wanted the probability of 60 individuals having private health insurance. This would be 60 factorial times 40 factorial. And then this P is the probability of success in any one event. So in this example would be the expected or the overall probability of an individual in the population having private health insurance. Obviously, in a sample of 100, that overall probability of having health insurance does matter for how many you expect to see. So that's to the power of the number of trials, and then 1 minus p to the n minus x. That's the binomial distribution. I'll upload another binomial distribution calculator that's kind of handy for doing this for some of the problems. Here are a few example realizations of the binomial distribution. So red here, this is n equals 20 events with a probability of 0.5. So you can see the expected number of successes is 10, half of the 20, but we have a symmetric distribution of successes centered around 10. What do you notice about this distribution and about these ones? Yeah, they look pretty normal. They look pretty normally distributed. It turns out that they are very nearly normally distributed, and we use that as a shortcut to the binomial distribution. Works out well because with small numbers, this normal approximation is less good. Like if n equals 5, you can imagine it gets truncated here because you can't have -1. You can't have -1 successes. So for small n, the binomial distribution is better. For large n, the normal approximation becomes very good, and it also happens that it becomes hard to calculate the binomial distribution up here because of those factorials. So as an example, the prevalence of diabetes in an elderly population, let's suppose it's 10%, so the p is 0.1. What is the probability that if we take any 4 individuals independently, not family members, not not all people who met each other through a diabetics group or something like that, what is the probability that exactly 3 of them will be diabetics? Here's just an example of using that binomial distribution calculation. Yes, question.
Factorial is, again, I'm not exactly clear on that. So that would be 4 times 3 times 2 times 1?
Yes.
Okay.
The factorial, 4 factorial is 4 times 3 times 2 times 1.
Okay.
By convention, 0 factorial is 1.
Okay.
And it's only well-defined for integers. So whole numbers, whole positive numbers. Question?
And so when you explain these in class, it's very clear. However,
Thank you.
To see an example like this on a test, like that during our exam, I wouldn't know what you were asking me to do. Like I wouldn't know that that's the formula I should apply.
Right.
It just doesn't come through that way. And maybe I'm the only person that happens for, but it just doesn't come through that way. And I don't know if there are clues or something about a question that will help you to realize that that's what you're needing us to get at.
Yeah, so I suspect this has to do with examples and identifying. So this is some math and probability stuff, and I've given you like 1 example or 2, but there are a million examples that I could choose from, and a lot of them sound different from the ones that we did in class. I would love to hear some other examples from you. I mean, I have limited I have only a certain amount of creativity to think of an example application of this. That's what I kind of think of as the solution to that is having more examples.
On an exam question too, would you say the probability of having diabetes is a binomial distribution?
No, I wouldn't say that.
Yeah, so you would have
Right.
to figure out from the context.
Right, it's not in the section under binomial distribution calculations.
Tricky.
Right.
Is there maybe a way you could write the binomial distribution equation with like the qualitative, the words maybe? So like instead of that 4, you would write the number of individuals you select.
4 individuals.
Or just not, it's kind of like have an intermediate step where you go from the different, values that you give in words and then put them in an equation in words also. I don't.
Yeah, I
So
can do
if you did
that.
that on a slide, that's
Mhm.
exactly where I would go if I was looking at an exam question.
Right.
Go to that slide and you interpreted it.
Yeah, take the
I don't know if it would translate.
mhm.
It's like the 3 is the x equals 3 is
Yeah.
that's the probability that exactly 3.
So maybe it would be useful to have, we had this, start with that, and then fill in the 3 people over,
Yeah, maybe
or
something
4
where it
people
would
over 3.
be more meaningful.
So,
Me, I don't know.
yeah. I'll give another example here, and then I want to hear someone else come up with an example too. Well, there was one from the last test that could have been done using the binomial distribution. You didn't have to, but you could, which was the number of elderly grandparents that you would expect to fall over a year, or what is the probability of a certain number of them falling. So the important pieces of information about that is that one of the outcomes, one of the grandparents, there's only 2 outcomes. It's either they fell or they didn't fall. And then we have multiple people who each fell or didn't fall independently, and we want a count of the number of them who fell. That is a perfect binomial distribution example.
I'm sorry, because that's what I was thinking when you did that. Like, why would that have been the answer to that question?
You could have done that using this. I mean, I hadn't shown you the binomial distribution yet, which is why I asked you for the probability of none of them falling or of 1 or more, because you could do that without as well, just by taking the product of the probabilities and get the same answer. I'm going to give you a spreadsheet that calculates this, and I think it's kind of helpful because instead of just calculating out all of this stuff, it just has this formula in a bunch of cells where you put in what n is, and then you put in your x, and you can actually see the probabilities for each of them. So if you have 4 grandparents, then you would have n equals 4, you would have x equals 0, 1, 2, 3, 4, and you would see the probability of each of those. And so then the probability of no falls, you would look under the x equals 0. Of 1 or more, you could add up the other columns, or go 1 minus the x equals 0 value. How about one more example of a binomial distribution application? Okay.
You're asking.
Yes, I'm asking for one. And you volunteered.
Yeah,
So how about like 10% of cereal out of a factory is tainted?
Yep.
And you say 1,000 people in the city bought it. What's the probability that 500 bought a tainted sample or a
Yeah,
tainted box.
good example. So tainted cereal or any sort of a food poisoning. If you have a certain number out of suppose you know that this factory sent out 1 million boxes and 10% of them were tainted, you might want to know what's the probability of having at least one poisoning case in a place where 10 boxes of these were consumed, or what is the probability of having multiple poisonings from this tainting.
Is
Yeah.
this how you do like responder analysis?
Responder analysis?
Yeah, like if you either succeeded or didn't succeed on a drug, and like what's the probability that so many people did succeed?
Yeah, that sounds like an example. I mean, each individual in a drug trial, if you binarize it and say that everyone either responds or does not respond to the therapy, the way this would really be used was, okay, we have 100 people enrolled in this trial. We know that our standard therapy, people have a success rate of 50%. We want to know, is the response rate for the experimental drug higher than 50%? And what you would do, your null hypothesis would be that it's equal to 50%, and you would say, what's the probability? We saw 60 people respond. What's the probability of that happening? If the true response rate.
Or like if you do a people go 0.5, right? Was it more than that? Like more rare?
Yeah. So let's.
This would describe that then?
This would describe that. Yeah. So we have a clinical trial where the standard of care measured over millions of people has been found to be 50% of people respond to it. Now we do an experiment with 50 people, or let's say 100 people only. This would be a bit unusual because usually you would control within the trial. You would have a control and a treatment within the trial. But if somehow the control were the entire population, and we want to know, are these 100 people responding differently than the entire population? We would take, I'm going to go back to this. Oops, that's the Z. We would take, let's say we had 100 people in the trial, probability of response is 50% from the population. This is what the binomial distribution tells us that the expected number of responses in this trial would be. So one time you do the trial, you would see 50, another time you might see 60, but the probability of that is lower. The probability of seeing 40 is the same as it was of seeing 60. And if we saw 60 and we want to know what's the probability of seeing 60 or more by chance, you would just actually take the probability for 60 plus 61 all the way up to 100. And if that were less than 0.05, you could reject your null hypothesis at 0.05. Yeah. Any other questions about whether something's a binomial distribution application or not? Okay. Thank you for asking that. This is just to point out that because these events are independent, we only use the binomial distribution for independent events. We can just add probabilities. So this looks a lot like the grandparents question, doesn't it? For individuals, what's the probability that at most one would be diabetic? So this is a little bit more complicated than what was on the exam, only in that you have to use the binomial distribution really to do this. Maybe you could do it without the binomial But certainly the easiest way, especially if you had a spreadsheet, is just to put in n equals 4, x equals 0, and x equals 1. You see these values for 0 individuals and 1 individuals out of 4 having diabetes, and just add them. And then conversely, the probability of at least 1, so not 0, not 1, but 2, 3, or 4, you can use that rule of total probabilities summing to 1 to calculate the others. So in this case, it wouldn't be much harder to calculate the probability of 2, 3, or 4 people having diabetes and add up those 3 numbers. But if it were like, you know, how many people out of 20, then it would be a lot easier to do it for 0 and 1, and then go 1 minus your result. In Excel, here's the function binom.dist. Anyone want to guess what the things are you have to give to the binom.dist function to get a result?
Number of trials,
Number of trials and
probability, the p-value,
the p, the probability. One more thing,
the
x, the number of successes. So in that diabetes example that I gave here, if you wanted to get these numbers in Excel, what are the numbers that you would enter? What would n be? Yeah, 4. What would p be? What's that?
like 1.
I forget, what was it? Yep, 0.1. 0.1, and here, what's x? This is probability of 0 individuals out of 4 having diabetes. That's x equal to 0. So that's the probability of none of them having diabetes plus the probability of 1 of them having diabetes out of 4. So in this case, we're calling success having diabetes, which suppose you wanted to do it the other way. Suppose you want to say success is not having diabetes. Can you think about how you would approach the problem differently? So suppose you wanted still the same answer. I can tell you that you can get 0.9 if a success is not having diabetes. And if we want the probability that at most 1 has diabetes, how would you say that in terms of the number of individuals not having diabetes?
4 and 3.
Yep, 4 and 3. So x would be 4 and 3. So we would still have n equals 4, but p would be 0.9, and x would be 3 and 4. And we would add those two things together, and you'd get exactly the same answer. Make sense? So point is, what you call the success, it's arbitrary. You can call either one a success. Usually you call it the thing in the way you're going to ask questions. If you're going to ask a question about how many people are diabetic, how many people have a fall, how many poisonings from a food tainting there is, whatever the thing is that you're counting, that's what you're going to call a success in the language of these Bernoulli trials. So you noticed how the binomial distribution looks very similar to the normal distribution. It is, and all you need to know is that the mean of that normal distribution is n times p. This makes sense, right? You know why the mean is n times p? So let's take the example of 100 people, 10% probability of diabetes. What's the mean number of diabetics? 10. So that's all this says. The mean is the number in your trial times the probability of each individual being a success or being counted as the thing that we're asking questions about. And the standard deviation is this thing, the square root of n times p times 1 minus p. So in that example, it would be n equals 100 times 0.1 times 0.9. So it turns out that a probability or prevalence around 0.5 has a larger standard deviation, it's broader, and something more like 0.1 or 0.9, it's narrower. There's a narrower range of what you expect. So, oh, here the example is 1,000 people, prevalence of 0.1. So the mean here, 1,000 times 0.01, that's 10. Wait a minute. Sorry, this is a mistake here. This is a prevalence of. So this should say, one of these days, I would love to find out how in this room to have my little writing tablet set up. So 0.01 or 1%. I usually prefer doing these probabilities as probabilities between 0 and 1 instead of percent, because these equations then work directly if you're using probabilities, whereas this standard deviation will be wrong if you're using percents here. It'll be 100 times 100, too large. Oh, let's see, there was a question. Oh my goodness. Apologies, everyone. I could not see your questions coming in. Z-score. Let's see, I'm going to go about answering some of these online questions. Would at least one not include one? Yes, I think at least one means one or more. Let's see, there was a question about the factorial on the outside, 4 minus 3 factorial. Yes, that is 1 factorial. Or 1. So the answer is 1 here. Annie? Maybe those are the only ones that I missed, except for z-score. I don't think I can answer that one anymore. I don't know the context. Okay. So the rule of thumb that we often use is if both n times p and n times 1 minus p are both 15, then the normal approximation is very good. It's still not bad if it's smaller than that. But if you have like a p-value somewhere close to 0.05, and one of these values is less than 15, so that's like an expected number of failures or an expected number of successes less than 15. Whoa. Okay, time to wrap up here. All right. And that's all for today. We went over some probability notation and calculations, a little bit of new probability stuff. And we're going to practice some more upper and lower tails of the normal distribution. And let's get down to the lab, unless there are any questions.